Thursday, February 24th, which among other things means that I have 4 days to figure out what I'm doing for my wife's birthday. Technically speaking, she doesn't actually have a birthday for another 3 years, but I learned a long time ago that if I want to keep my relationship going, the excuse, but honey, you only have a birthday on leap year, so you don't actually have a birthday this year, does not win me a lot of points. And so instead, what I do is throw an extra big party on the year she really has a birthday, and then celebrate the entire week surrounding where her birthday would be on the other years to make her feel better about not having an actual birthday. So it works out doubly great. Anyway, enough about my personal life and issues. As far as you guys, things you have to worry about, unless you have a leap year baby in your life, is that the homework in the lab need to be in today by 1700. And then as a reminder, we don't have class on Friday because you guys will all be becoming better leaders through your conference. But that does mean since we don't have class on Friday, we do have class on Monday next week. It's going to be really weird for me to have class 3 days in a week because that hasn't happened for a while. But we have a quiz on Monday. And I say on Monday, but really, like before, it opens on Monday, right? So you can do the quiz anytime starting 7 a.m. on Monday until 1700 on Tuesday. And I will double check, but it should only include things up to our last lesson. So not this lesson. Confidence intervals, sampling distributions, central limit theorem, but not hypothesis tests like we're going to talk about today. Okay, I think that is my main stuff that I had. Do you guys have any burning questions that you wanted to throw at me before we got into hypothesis tests for today?
Yes, sir. I got a question on the lab on how the R binomial deal would work on question number 5.
Sure. So here, real quick, because this has come up more than once, as a reminder, R binom, if I say R binom and I say n equals 5, size equals 10, and prob equals 0.6, what that is going to do is that generates 5 sample numbers. And what those are is that is saying, let's assume I have a binomial distribution. Wow, where apparently I can't spell size. Somehow it still let me get away with that. Where I have 10 trials and the variable is the number of successes I get out of 10, given that the probability of success for each trial is 0.6. And so what this then does is generates 5 different numbers, right? And I got 66767 here, right? Because I'm saying that I've got a 60% chance of getting any one right. So it's reasonable that in general, I'm getting 6 right more than others. If I did, 50, I would get 50 samples. And now I'm every now and then getting a really low or really high because it's possible, but just unlikely. And that's what R binom does, is it generates a bunch of sample versions of the variable based on the size and the probability. Does that answer your question, or did you have a more specific question about how R binom works?
How to integrate it, because I'll put it in there and then it spits me out 0.
You mean when you mean integrate, you mean how do you work it into the problem?
Yes.
So what without just telling you exactly how to do the problem, in the particular question, it's basically saying, hey, you guys are going, you and a bunch of friends or a class, depending on if you're looking at question 2 or 4, are taking an exam, and you want to simulate your exam scores, and how many questions are in each exam and the probability that you get each right? So n would be the number of exams that you are simulating, size would be the number of questions on the exam, and prob would be the probability of getting any one question right. And so by then doing this, you would generate a certain number of simulated test scores, right? And then what you want to do with those test scores depends on what your question asks, right? And so in the question, it says, do that 10,000 times, right? So that means you're going to have something like where it says for I in 1 to 100, if I ran this, then this is going to, everything in the braces, it's going to do it 100 times, right? And so what I can do is I can do things like, if I wanted to know, if I said up here, if I made some variable where I said, I don't know, worst equals numeric 1,000. That's going to make a empty list with 1,000 spaces. And then here I could say, or actually I'm only doing 100, so let's make it 100. Down here I could say, every time I run this sample, then what I want you to do is I want you to go into the ith space of worst, and I want you to store there the minimum value. And in fact, I'm going to say here, let's say test scores equals that. And then I'm going to say in here, I want you to write the minimum value of all of those test scores that you got, right? And so if I were to run this code, then what it's going to do is 100 times, it's going to simulate 50 test scores, and then it's going to take the minimum of those test scores and put it into the worst, so that now when I look over here at my variables, you can see that the worst variable is filled with whatever the worst score was out of each of those times that I tried. Does that get closer to helping you get on the right path of what you're looking for?
Yes, sir.
Cool. If you struggle more later, feel free to, I'm teaching all day today, but if you want to send me a message with a screenshot of code or something, I can definitely probably push you back on the right path without too much trouble. All right. So speaking of hypothesis tests, so as a reminder, this is where we left off last time, right? We talked about confidence intervals, and we said we went through both what they, why we had them, how we found them, and then we looked at some code from them. Based on what we talked about last time, and if you guys spend any extra time looking at the guided lessons or downloading that code that I had, does anyone have any additional questions that they wanted to bring up today that didn't come up yesterday on confidence intervals? And I say yesterday, but I mean Monday. Okay, so Monday was confidence intervals. Today we're talking about hypothesis tests, and they're related but different. And hypothesis tests are really, without trying to oversell it, like hypothesis tests are why statistics exist, right? Statistics are like, that's the main like thing that we create with them, okay? So in a confidence interval here, like it says at the top, we don't know the actual parameter. So what we do is we get an estimate, and then we build an interval around that estimate and say, hey, here's how confident we are the actual number is somewhere in there, right? For a hypothesis test, we approach it a little differently. In a hypothesis test, what we say is, I'm assuming the actual parameter is some value p naught. So I'm saying, I think I know what the real parameter is. Then, and I just assume that. Then what I do is I take a sample, get an estimate, and then by analyzing that estimate, I then decide whether or not I have significant proof of whether or not I should reject that original assumption that I made, right? That's what a hypothesis test is in a nutshell. I make an assumption, I take an estimate, and then by analyzing this estimate, I decide whether or not I should reject this original assumption or not. That's what a hypothesis test is. To give it a kind of an idea of this, I feel like it's probably easier to work through a concrete example, and then we can talk about seeing questions afterwards. You can ask questions in the middle of it, but I just figured by showing how this works, you might be able to solidify any questions that you have at it. So let's use an example with my brother. You guys don't know, well, hopefully it'd be weird if you knew about my brother, but I have a younger brother who's 2 years younger than me. His name's Noah. I have 2 younger sisters too, but I have spent far more time with my brother because we had to share a room for 17 years when we were younger, and not a really big room at that. And it turns out that when you share a room with someone for that long, you both become very good friends, and you also want to kill each other every now and then. It's a lot like being married. So this is not an unlikely scenario. We played Risk a lot. If you guys have ever played Risk, it's a board game where you're trying to take over the world and you simulate battles by rolling dice, and higher numbers are better, right? So it is very reasonable to believe that after beating my brother in one of these games of Risk that we played a lot, that he threw a tantrum because he's a child and accuses me of cheating because I rolled so many sixes. He's basically claiming that, hey, there's no way you could be that good. Spoilers, I am. And that the dice must be weighted. It's not fair. And that he's going to go tell my mom to grab me, which this is a fictional scenario because my mother knows I'm a very good child and she would never actually grab me. But this is for the sake of mathematics. Let's pretend that my mom would consider that maybe I was a cheater. So in this scenario, we're going to define a bunch of things. Some of these we've already talked about. Some of these are going to be new. So the first one is we have to talk about what is our parameter of interest, right? And I'm not saying we need to say what it's equal to. We just have to say what is it describing. So in this case, the parameter of interest, the parameter we care about, P, is the proportion of rolls that my dice comes up 6, right? How often, of all rolls, what is the actual fraction that it comes up, right? Because he's saying that the dice is weighted. So we're arguing over what proportion of the rolls comes up as a 6. So that is the parameter we care about. Then we talk about the null value. So the null value, or what we call P naught, right? That's how I read that right there. That is P naught, P sub 0, P naught. And we don't mean not as in N-O-T. It's not as in I barely can spell American, let alone English. I believe it's N-A-U-G-H-T or N-O-U-G-H-T. Anyway, it's the English version of nothing, right? And so P naught, this is saying in the absence of any other evidence, what do we assume to be true? And we assume that the dice is fair, right? And so if the dice is fair, then that means that the 6 should come up 1/6 of the time, which is about 0.16, right? So our null value for P, our P naught, is going to be 1/6. We're assuming that it's fair, okay? Along those same lines, or not along the same line, I'm sorry, but the next thing is our sample size, which in this case, it's the number of rolls that I made, right? The actual population here would be, I'd have to roll the dice an infinite time, right? Because I'm saying if I wanted to know the real proportion, it would mean of all the possible dice rolls, of all infinite dice rolls, what's the proportion that comes up 6? We don't have the time to do that, so we're doing a sample. And we're going to assume that because my brother is petty and pedantic, that he has actually kept meticulous care of how many times I rolled the dice during the game. That's our sample, right? And from that sample, we can calculate the point estimate, right? We don't know the real P. We're going to assume that it's this null value, that it's fair. But our estimate is the fraction of 6s in the sample. So again, going back to my brother's petty records, we're going to say that he counted how many times I rolled the die, and then he counted how many times I got a 6. And the number of times I got a 6 divided by the sample size is our P hat. That's our estimate of the parameter of interest. Any question on what we've got so far and what we're setting up? Okay. Now we're going to get into some new terms that we haven't seen up to this point. And the first one is null hypothesis, or H naught, right? And so this is the hypothesis is, something a theory we're putting through, or assumption, or something like that, right? And so the null hypothesis is that we are assuming the die is fair. It's the thing. What is the thing that we assume to be true up until this point, and if nothing changes, that we will continue to assume after, right? It's the thing, if nothing changes, that we have believed and continue to believe, which in this case is that the die is fair, right? That is the null, the basic, the assumed assumption. H naught is the die is fair, or another way of saying it, I could write this mathematically as saying my null hypothesis is that P equals 1/6, right? That is our null hypothesis. Our alternative hypothesis, I think I wrote it as alternate, it's supposed to be alternative hypothesis, or H sub A, is that the die is weighted so that I roll sixes more often, right? So another way of writing that mathematically is that H naught, or I'm sorry, H out A, my alternative, is that P is actually greater than 1/6. Now you can have different alternative hypotheses. I mean, they have to be related to the null hypothesis. Like I said to the previous class, my alternative hypothesis in this scenario can't be that, you know, Lady Gaga is a great singer. That's a hypothesis or a fact. But it has nothing to do with the null, right? The alternative is something that would disprove or can't be true at the same time as the null hypothesis. That being said, I could do different versions of this, right? My brother only cares if the dice is not fair, but I am getting sixes more than I should, right? And so that's why it is his alternative is that P is greater than 1/6. Now, if for some reason me getting sixes was a bad thing and helped him, then he might say, oh, no, you're cheating. You're not getting enough sixes. And so his alternative hypothesis would be that P is less than 1/6, that the proportion of sixes I get is lower than it should be. If he was on the other hand, if he was a casino owner, then what he would probably care about is that he doesn't care if P is greater than 1/6 or less than 1/6. All he cares is that it should be equal to 1/6. And so his alternative would be that the die, that P is not equal to 1/6, basically saying, I don't care if the proportion is lower than it should be or higher than it should be. Both of those are bad. And so my alternative hypothesis is that the actual proportion is anything except 1/6, right? And we'll talk later, but that's the difference between a one-tailed hypothesis and a two-tailed hypothesis. But in this case, we are doing a one-tailed. He only cares if it is bigger than 1/6. Okay. Questions on the null and alternative hypothesis and what they represent? Awesome. Okay, so now we're going to talk about types of error. Oh, I'm sorry. I don't know why that popped up. Let me put this. Get over here. My computer moves very slow. Okay, so hold on a second. Getting what I can only imagine is a very important message. Well, you are driving me crazy, computer. Okay, so sorry, I'm back. All right, so ultimately, we are going to make a claim, but and this is one of the things that is most aggravating to some people for statistics, is that we can never be 100% sure. We are not going to end by saying Chris definitely cheated or he definitely didn't cheat, right? We are going to look at the data and we're going to make a statistical claim, but we might be wrong and we will never know whether or not we are actually wrong, right? Because whether or not we are actually wrong depends what the truth is about the die. And unless we're God, we can never actually know what the true truth is about the die. We'd have to roll it an infinite number of times, right? So we have up here, right? We have, if we consider reality, right? Reality is either that H naught is true or H naught is false, right? One of those things is reality. I don't know what it is. If H naught is true, that means the dice really is fair. If H naught is false, then that means the dice really is not fair, right? Regardless of what the truth is, we are going to make a conclusion. We are either going to reject H naught or we're going to not reject H naught, right? And so one of several things is going to be true, right? If, whoops. And actually here, I'm going to, let's make this just because I wanted to match up with your book. I think this looks like this, and this looks like this, right? Okay, so if H naught is true and we don't reject it, great. That is the right decision, right? Because we're saying, hey, H naught really was true. The dice is fair. And we made the decision to say, hey, I can't say that's wrong. And we were right. So good for us. The other option is I could say, hey, I don't think H naught is true. I reject it. And it turns out that in reality, H naught was false. And so again, I made the right decision. That is good. Those are the places that we hope we are. However, it's possible that maybe H naught was false, and I'm sorry, let's say H naught is true and I reject it, right? That puts me down here, right? And so that is what we call a type 1 error, meaning H naught was true, but I looked at my evidence and said, I don't think it's true. And I said, I reject it. I've made a mistake then. And that is called a type 1 type of error. The other type is type 2, right? And type 2 is that H naught really is false, but we fail to reject it, right? And that is a type 2 error up here. So in respect to our scenario, a type 1 error would be that we decide that I am cheating even though I really wasn't, right? H naught was true, but we come to the conclusion that it wasn't. And so that's where I unfairly get grounded. Type 2 is where I get away with cheating. It really was not fair, but we came to the conclusion that we couldn't say that it wasn't, and we don't reject the null hypothesis, and we say, sure, it sounds like it's okay. So that is type 1 and type 2 error. We don't like either kind, but we can't completely eliminate the probability of making them. All we can do is try to lower the probability. So let me ask Michaela, are you online? No, Michaela. Who else do we got? Who else do I have on my list? Here. What about Sierra? Are you online?
Yes, sir.
So this is just a matter of opinion. Both answers could be correct. If you had to make a type 1 error or a type 2 error, which do you think is a worse kind of error to have to make?
I'm gonna say type 1 or no, type 2. And that's what I'm gonna go with. Final answer.
Okay, so type 2. So are you coin flipping it here, or do you got any opinions? So in type 2, in my scenario, you're saying it's better that we ground me even though it was fair instead of letting me, because type 2 is So I'm sorry. So you're saying you would rather make type 2 or you'd rather make type 1?
I would rather make type 1.
Okay, so you'd rather make a type 1 error. So you would rather that I get in trouble even if it was really a fair dice, instead of me getting away with cheating. I mean, my brother would agree. My brother would agree with you. And so yeah. So from so she's taking my brother's point of view, right? She's saying, look, I would rather be mistaken so that he gets unfairly accused rather than him getting away with it, right? And that's kind of opposite of what we do in the legal system. And so in general, most times we do care more about type 1 error, because to make an analogy, it's like type 1 error is sending an innocent man to prison, whereas type 2 error is letting a guilty person go free, right? And most people are more concerned if they would rather let someone guilty free than send an innocent to prison. That's a bit of an extreme example, but that's kind of, to give an example and less like legal, think of it this way. Type 1 error means that the null hypothesis is what we've been doing forever. And if we don't reject it, then we don't have to do anything different, right? So rejecting the null hypothesis means we were wrong and we now have to do something different. And doing something different usually costs money or time, right? So think of it as like saying, hey, the military, the null hypothesis is that there's nothing wrong with the gas tanks in all of the cars. The alternative hypothesis is that there's a crack in the fuel tanks, right? And so type 1 error would mean that we said, hey, the fuel tanks aren't okay, even though they actually were, right? So if we make that type 1 error, that means we spend all the money and time to recall all the cars and replace all the gas tanks, even though there wasn't a problem. And so people don't like making type 1 error, because if you make type 1 error, that means you are spending money and resources that you didn't have to spend, right? Whereas type 2 error in that same situation would mean we looked at all of them and we decided, hey, we don't reject. We can't find enough proof that there's any problem with the gas tank. And so we don't, even though there really was. And so that means we don't have to spend any money and time. And there really was a problem, but the problem was so small we couldn't notice it. And if the problem was that small and we didn't notice it, we can probably keep on going. And worst case scenario, it gets worse in a couple of months, and then we have to spend maybe a little bit more money to bring everything in, right? But in both cases, we spent the money. In one case, we spent it unnecessarily. Now the problem was so small, we didn't have to deal with it till later. So type 2 is usually less of a problem, right? But Sierra is right. Sometimes we care about type 2 more than we care about type 1, because if we, instead of thinking about it of gas tanks on a car, what if we think of it as the casing on the nuclear material in a missile, right? If we have a type 1 error, that means there really wasn't a problem, and we spent all this money to replace all the casing, but we're still all safe, right? We spent some money, but we spent the money unnecessarily. Whereas on the other hand, if we made a type 2 error, we saved the money, but maybe there was a microfracture in the casing and nuclear radiation is slowly leaking out, and that could either cause a catastrophic problem, hurt people, or maybe our missiles just aren't ready when we need them, right? So in that case, a commander might very well say, I'm more concerned about type 2 error, because type 1 error means I spend money that I didn't have to. Type 2 error means there's a possibility that I have catastrophic issues. And so I would rather mistakenly spend money than miss a problem that could cause bigger problems. So depending on what we care about, type 1 or type 2 might be what we care about. The problem is if we minimize one type of error, the probability of the other type of error goes up, right? So because we usually care about type 1 error, we call that we call that the significance level, alpha. Alpha is the probability of type 1 error. And so usually we want to make alpha smaller, because the smaller alpha is, the smaller the probability of making a type 2 error is. However, the smaller alpha is, the bigger the probability of type 2 error is. And so if we want to make type 2 error smaller, alpha has to get bigger. And so it's this trade-off of deciding what you care about. In general, the standard alpha is 0.05. So if a question doesn't say anything about the alpha, you can assume that the standard alpha is 0.05. That's usually, in the absence of any other information, we're okay with a 5% probability of type 1 error. If you can, sometimes you'll see 10%. Usually you don't see much higher than 10%, because above 10%, if you tell someone, hey, my alpha is 20, they go, okay, so there's a 20% chance that you made a type 1 error. I don't know if I feel good about this research. 10 is okay. 5 is the standard. Anything below 5 gets better. If you can say my alpha is 1%, or in some cases 0.1%, then people go, whoa, okay, so you're not sure, but you are pretty dang confident. Okay. Questions on type 1 and type 2 error and how the significance level relates to that. Okay, so now we get to the last part, which is the important part, and it has the equations on here. So the p-value, and this is kind of a mathematical way of saying, and we'll show kind of this through a picture and some code in a second. The p-value is the probability that you would get an estimate. In this scenario, it's the probability that you would, if x is any possible estimate from a sample, then it is the probability that we would get an estimate bigger than the estimate that we got, right? If H naught is true. And so to put that into pictures, if I were to keep taking samples of rolling the dice over and over again and counted and measured the proportion of sixes, we know that I would get this histogram where all my estimates would be start to look bell-shaped and be centered around 1/6 if it was fair. We know that if the central limit theorem holds, that actually converges to the normal distribution, and I can say it is normally distributed because this down here is saying x is all of my possible estimates. And so really, I could say, you know, x is all possible p-hats. All the possible estimates I could get are distributed according to this normal distribution. And so to decide whether or not I believe that the null hypothesis is true, that the actual value is p naught, is what I do is I say, okay, pick an alpha. And so I say my alpha is something like 0.1 or 10%, right? And so the area here is alpha. That's the probability, right? And so I say, and then I make a estimate. I take a sample and get an estimate, and then I calculate what is the probability of being that far or farther away. In this case, not just that far or farther, but that high or higher, because my brother only cares if I am higher. And then I say this area, that probability is my p-value. If that area is, that probability is less than alpha, then what I am saying is the probability that I would get an estimate this far away or farther is less than alpha. It's smaller than alpha. And so I'm basically saying the probability that I would get this estimate is smaller than the alpha we agreed upon, and therefore it is very unlikely that I would get this estimate, and therefore I reject the null hypothesis, because it is a small, if that was true, there's a small probability that I would have gotten this estimate. Therefore, I think it is likely that the null hypothesis is true. I say, like we say up here, I say, I have significant proof to reject our assumption or our null hypothesis. And that's what that's how a hypothesis test works, is we use, if I got it, yeah, go ahead.
You just said that we reject that the die is fair. I'm still confused on why we can do that, because you just said that the assumption is true.
We reject.
Getting,
Sorry, you say out what the problem is, and I will explain either I misspoke or there was a misunderstanding.
I don't know. I'm just confused, I guess, because we said that if we're that far away from having a expected value of 1/6, meaning it's a fair die, for our P sample, are you saying that means it's unlikely that it's fair because it's so far away from what we should expect, even though it's a sample?
So think of it like this. If the dice is fair, we expect to see a distribution of estimates like this. When I roll the dice, every time I roll the dice a certain number of times, I don't expect that exactly 1/6 of them are going to be 6. I'm going to get and I know that every time I take a sample, I'm going to get a different estimate. However, this distribution says there's a large probability that I should get an estimate close to 1/6, right? The area under that curve represents the probability. So whatever that area is, that's the probability that I should get a estimate from here to here, right? And so the further I go out, I can say, there's a 99% probability I should get an estimate somewhere between this number and this number, right? And so what I do is I establish an alpha and say, look, here's my alpha. Maybe this is not to scale, but let's say that's 10% probability, right? Which means there is if this was true, there's a 10% probability that I would get an estimate this high or higher, right? Then I take my sample and say, okay, let's get an actual estimate, and said, I got this estimate. And then I say, well, there's this percent probability that I would get an estimate that is this far farther away. And so if that probability is small enough, I say, hey, that is such a small probability that it is unlikely, if this distribution is true, that I would have gotten that estimate. And so it is more likely that distribution is not true, which means that this is not true.
Okay, I see now. Thank you.
Definitely. Yeah, I apologize. I was talking fast and I very well may have misspoke on something there. Okay. We've got about 10 minutes left. I'm going to switch over to code for this problem, but please interrupt me if you got questions, and we'll definitely talk about this next time. I just wanted to make sure you guys got a chance to see the code and then know that I'm going to definitely post this so that you can play around with it. So this is the same scenario that we're just looking about my cheating brother, and we're going to use the same prepare, check, calculate, conclude that we did before. We're going to start using that more often in the next couple of lessons. So prepare, our parameter of interest, what is it? It's the proportion of dice rolls. Our null parameter, that's our P naught. That's 1/6 because we're assuming that's what it is. Our null hypothesis is that P equals P naught, that it's fair, that P is 1/6. Our alternative hypothesis is that P is greater than 1/6, right? My brother only cares if it's unfair to him, right? He's not a casino owner, so he's doing what's called a one-tailed hypothesis test. So he's looking, his alternative is that P is greater than. I'm not going to go into it depth right now, but if he was a casino owner, he would say, I just care that it's not. So I want to know if it's that high or if it's that low. So I would have to take this and multiply it by 2 to say, what's the probability that I would be that far or farther away? That's what you guys were doing in lab 5, is doing a two-tail, because it says, hey, what's the probability that you would get an estimate this far or farther? So you would need to do both the tails. Then we have to identify our significance level. Most problems will just tell you the alpha is, we're going to do this test at a alpha of 0.05 or an alpha of 0.1 or an alpha of 0.01. If it doesn't tell you anything about it, you can assume a standard level of 0.05. In this case, I kind of said, well, what makes sense? And so in this sense, type 1 means that the die was fair and I was mistakenly accused of cheating. Whereas type 2 is that I actually was cheating, but I mistakenly got away with it, right? My brother is more concerned about type 2 because he wants to lower the probability that I get away with cheating. And because of that, he wants the alpha to be higher than normal. So instead of taking the standard alpha of 0.05, he's going to insist on an alpha of 0.10. So I'm not saying that in a question like this that I would expect you to choose the alpha. I'm just saying that's how he chose the alpha. So that's why our alpha is 0.10 in this case. Then we're going to identify our sample size. My brother says that I made 152 rolls, so that's our sample size. Identify p hat. He's saying I did 31 sixes, and so 31 down here is the number. So 31 divided by 152, that is my p hat. And you can see over here on the right, my p hat, the estimate is 0.20. So actually, my brother might have a case, right? We're supposed to get 1/6 of I'm supposed to get sixes 1/6 of the time, but it looks like I actually got them a little over 1/5 of the time, right? But that doesn't mean I was cheating, right? The estimate can vary. The question is, did it vary so much that it is likely that it was the proportion, the null hypothesis is not true? So that's what we're going to test. So then we do the check conditions. Which are they independent? Yes, these just came from random dice rolls, and so that's a random sample, so they are independent. And then we say, is the sample size sufficiently large, which is checking these two inequalities, right? But unlike the confidence interval where we said, hey, I don't know p, so I'm going to use p hat to estimate it. Here, we know p, right? Because we don't really know p, but we are saying under the null hypothesis, we are assuming that p is 1/6. So we're going to use that null value, p naught, which is 1/6, as our p, because we're assuming that's what it really is. So I run that, I get 25 point a bunch of numbers, 125 point a bunch of numbers. They're both bigger than 10. Conditions are met. Awesome. I can use the central limit theorem. Any questions on what we did in prepare and the check steps? Those are probably the easier ones, but they are ones that you got to make sure you do all the steps for. Just because they are easy, you can't just skip over them. We still have to lay the groundwork for the later parts to work. Okay. So now we're going to do calculate. We're going to calculate, starting off with the same thing in the confidence interval. We're going to calculate the standard error, right? But again, I don't need to use p hat as my estimate because I am using my assumed value of p naught, which I am assuming this is true under the null hypothesis. So I'm going to use p naught everywhere here where I would for p, calculate the standard error, same as we did before, and there's my standard error, 0.030. Okay, now here's where things change from the confidence interval to the hypothesis test. Because now what I'm going to do is I'm going to find a z-score. And all the z-score is how many standard errors away my estimate was from the actual value. Remember? And we introduced z-score. I don't know if you remember, but when we very first introduced the idea of a normal distribution, we talked about a z-score of saying it was a way to compare any two normal distributions, right? Because it was a count of standard errors, right? And so if we look at this idea here, what the z-score is it says, hey, find what this distance is and then divide it by the standard error so I know what that distance is in terms of how many standard errors away my estimate is, right? So when I go over here, that's all that's happening to find the z-score is I say, take my estimate, subtract off what I am saying the actual p-value is to see how far away I am, and then divide it by what I found the standard error to be so that my z-score represents how far away, how many standard errors away from the p naught that I am. And in this case, I get 1.273. So I am about 1.3 standard deviations away, right? And that is good information because now I can basically, I'm now going to say the question, I'm going to ask the question is, how unlikely is it to be that many standard deviations or more away from my value. If it's a very low probability, I'm going to say, hey, I reject my null hypothesis because this is very unlikely. If it's low, then I'm going to say, if it's higher, I'm going to say, oh, it's a likely probability, right? And you guys know enough about standard deviations, standard errors, same thing, that if that number was higher, we could already almost be sure, right? Because if that number was 3, you guys know that if you go 3 standard errors away from the center of a normal distribution, that includes 99.9% of the data. And so you know that before I even calculate it, that it would be very unlikely to be that far or farther. And so even without doing the calculation, you can say, oh yeah, no, we're going to reject here. That's definitely too far away. But 1.27, we're not sure. So let's do the math. We do the math anyway. And so what I'm going to do down here is I'm now going to calculate that p-value, right? And so that p-value right here is, I'm going to say the z-score, I'm going to say 1 minus, I want the upper tail in this case. So I'm going to say 1 minus p-norm of that z-score, right? Because when I don't give a mean and a standard error, that's the standard normal, right? And since I have this in number of standard errors, I'm basically saying, hey, imagine a standard normal. If I go that many standard errors to the left, I'm going to get that value. 1 minus that value is going to give me that tail, right? And as long as I'm counting standard errors, the probability of that tail is the same across anything, right? I could, and this is how we normally do it, I could calculate it directly, right? The probability of being bigger, of being higher than that p-hat, I could calculate directly by saying, hey, 1 minus, and then use p-hat, and then use our actual mean and our actual standard error, right? And if I run both of those, I get the same number. This is just the way we usually do it because, well, partially because it's been the standard for like over 100 years to calculate that z-score, because we used to not be able to calculate things directly like you guys can. But also because by calculating that z-score, it's a convenient way of saying, hey, this is my z-score. That's how many standard errors away I am. And if you do this long enough, you get an idea of how many standard errors away is a big deal, right? And so by just giving that number, I don't need to know anything about the actual distribution. I just know, oh, 1.27, that's not bad. 2, 3, okay, that is really far away. So that's why we use the z-scores. But it is totally legitimate and fair to calculate my p-value in either of these ways. And then once I have all of that, I just put it all together, right? So there's a little script I wrote that just summarizes all of the numbers that we did and say, hey, here's this, here's the null, here's the sample size, here's all of this, but then says, what does that mean, right? And so what that means is my brother set out to try to prove the alternative hypothesis, right? That my die is weighted and that the proportion of 6s is higher than it should be, right? However, our p-value, which is right here, which is 0.1013, is higher than our significance level, our alpha. We said that our alpha was 0.1. And so my brother must say that there is not significant evidence to reject the null hypothesis that my die is fair. So he has to say there's not enough evidence to show that the dice is unfair. In a kind of non-mathematical term, what we're saying is the p-value is saying there is a bigger than 10% chance that if the dice was fair, I would get that big of a proportion of 6s or bigger. And since we decided on a significance level of 10%, we're saying that probability is high enough that we can't say that it's unfair. If my p-value was lower, if my p-value had been something like 0.05, then what we're saying is there is a 5% chance that if this dice was fair, I would have gotten an estimate this big. And we would have said 5% is smaller than 10%. And so now we're saying, based on the alpha we said, that probability is too small to believe that it could be true with the null hypothesis. So we would have rejected the null hypothesis. But in this case, our p-value is bigger than alpha, so we do not reject. Okay, I raced through that last part because we are 2 minutes away. But does anyone have any either quick questions or things they want to scroll up on, or anything you want to throw at me so that I can mull over and make sure I get answers back to you on the next class or in between? All right. I will definitely hang out for a couple of minutes if you guys are mulling something over and something jumps out on your question. But otherwise, in the meantime, like before, I highly encourage that sometime before Monday, you try downloading this code and toying with it and looking at it with the slides and the guided lesson to see what does it doesn't make sense. If you get a result that doesn't make sense, write it down and either shoot me a message for me to try to respond or think about it for class on Monday, or just bring the question on Monday, because we'll start with this before we move on to the next section. But in the meantime, focus on making sure you get your homework and your labs in. Tonight, make sure you're feeling good, or at least have questions that you need answered to feel good for the quiz on Monday or Tuesday. And then try to spend at least a good part of the weekend enjoying the NLCS. Spend some time not thinking about me and math, because there are more important things and other things besides that. But otherwise, unless I see you before then, I will see you on Monday morning. So have a great weekend if I don't talk to you before then.
Thank you, sir.
Of course.
Thank you, sir.
Yep.